Okay, so we're going to be looking at this formula over here where you have the force is equal to Q. This Q here is the charge on the particle. Alright, so if we're dealing with an electron, that charge would be 1.6 times 10 to the negative 19 coulombs. If we were dealing with an alpha particle, which is quite often a particle that is available, an alpha particle is like a helium nucleus. For those that do chemistry, it's got 2 protons, 4 nucleons, 2 neutrons, 2 protons. It's a 2 plus particle. It would equal 2 times this, 3.2 times 10 to the negative 19 coulombs. So this Q over here is the charge on the particle. The V, this V here is the velocity of the particle. Alright, how quickly the particle is moving. We can actually work that out quite easily if we know the potential difference that the particle actually goes through. We can work out the velocity of that particle. That's obviously in meters per second to the negative 1 in my SI units. The B, as before, is the strength of the magnetic field. And the combination of those three, when you multiply the three of those, gives the force, provided that the direction of the particle is at right angles to the direction of the magnetic field. So this angle theta here is let me go over here. The angle theta is the angle between the directions of the magnetic field and the particle. Okay, so if you've got your magnetic field going in this direction, if that's your magnetic field B going in this direction, and you have your particle going in this direction, maybe your electron going in that direction, you've got 90 degrees. And the sine of 90 is 1, so that works out to be 1. As soon as it starts changing direction, say if it goes in that direction over there where that's theta and that's your electron now, then obviously that force actually decreases somewhat as it goes. When it's going in the same direction, if you've got your electron going in the same direction as your magnetic field, your theta is equal to 0 and there is 0 force. No force is acted upon it. Okay, now let's just have a situation, say. Let's just say we've got this situation where we have our magnetic field is coming out of the board. Now the way that we show that is just as we did with currents. We can just put a dot and a circle, and that will be showing that our magnetic field, say I've got a uniform magnetic field, is coming out of the board. Like that, and we would put a B on it like that. That should show, if I've got a B next to it, that will be showing my magnetic field is coming out of the board. So this dot with a little circle also works for the direction for a magnetic field. So we've got a magnetic field coming out of the board, and let's say we shoot across it in this direction. We shoot across it an alpha particle. Now that's a 2 plus particle with a certain velocity. It's got a certain velocity. Now, what will be the direction of the force on this particle? Now, we use exactly the same rule as before. The thumb in the direction that the positive charge would make. The field is coming out. So we've got our field coming out of the board. Thumb in this direction. We're going to have a force downwards. Down. Okay. Thumb in this direction. Field out of the board, force down. Okay, so we'll actually have a force downwards like that. Now, it's quite interesting because that force that is acting at right angles to the direction is the centripetal force that we studied in Unit 2, which caused circular motion. So what's going to happen to this is that it would start to do this. Let's just have a look at the alpha particle at this point over here. Let's just say it's going now in that direction over there. So I'm looking at it at this point over here. Alright, now we've got it going this way. Field is coming out. The force is like that. So it continues to be at right angles, the force. And if this magnetic field extended all the way down, if I could extend this magnetic field down so it was still within the magnetic field, what would actually happen here is that we could get circular motion. Depending on the speeds, we could get circular motion happening. Alright. Well, if I take it over here, say the particle's over here, now it's going in that direction. Alright? So now it's going like this. Field out, force would be up. So your force there would be up. So it's always towards the center motion. So that's a centripetal force. And we can actually use this formula over here, that force is equal to mv squared over r in our formula. Where this force over here can be worked out from this formula. F is equal to mv, sorry, not mv, qv b sine of theta. So we can use that force in there. We know what our V is. We probably know what our mass is. We can calculate what our R is. How they actually discovered the masses of particles is that they worked out what this force was. They knew the charge. They actually measured the R, and from that they found the mass of the subatomic particles. And that is called the Baines-Bridge mass spectrometer, which higher level students will study, how that actually works.